Hello, my name is Rob Sides. I'm the Director of Marketing and Product Management at AMETEK Scientific Instruments. You may know AMETEK SI through the brands Princeton Applied Research, Solartron Analytical, Signal Recovery. Today's presentation is going to highlight different electrochemical test methods and products for the evaluations of lithium-ion batteries and supercapacitors. We're going to talk about DC test methods, AC test methods such as electrochemical impedance spectroscopy, and scanning probe technology. So when we discuss the diverse field of electrochemistry, we categorize it in three different main applications, key areas of focus. One being energy, the other being corrosion, and the third being physical electrochemistry. Within the energy segment, though, there's a lot of different types of technologies. These can be batteries, capacitors, fuel cells, or solar technology. A lot of the interest that the energy segment is garnering today is discussion and innovation in the terms of electric vehicles. And so I like this graph because it compares the power density and energy density of these different technologies. You can see represented here are capacitors, batteries, fuel cells, and then the comparison to where the gasoline internal combustion engine lies. So the y-axis here is power density, so this is going to be higher current, and the x-axis is energy density, and so this is going to establish kind of like a longer run time in an electric vehicle application. Note the fact that these are log scales also. So let's start at the top left, and let's look at the how capacitors can benefit this application. And capacitors have a high power density but a low energy density. And this is not surprising really to people with a physical electrochemistry background, because we know that when we put a voltage step on a capacitor, it's going to cause a large amount of current, but it's going to decay quickly. And that's represented here similarly with a high current, or basically a high power density that decays quickly. Batteries, on the other hand, while they don't have quite the power density of capacitors, they have a much better energy density. So you can see from a battery application where you would benefit from both capacitors and batteries in a combination type system, as you're looking for both acceleration and long run time. Fuel cells are an interesting place as well, because they'll functionally run so long as you continue to supply them with fuel. That shows a large energy density, and again that lower power density. And there is the gasoline engine there represented as a comparison. So let's look at the characteristics of some consumer products that we're all familiar with, and let's use it to identify trends in research and market demands. So this is going to introduce the term capacity. Capacity is written, it's a measurement of charge, unit of charge, and it's written in terms of amp hours or milliamp hours. And so now if I take this consumer product of a cell phone, if I can look at the battery associated with the BlackBerry, the iPhone 5, the iPhone 5S, the iPhone 6, and now we can look to see what the capacity ratings do of each one of these battery technologies. First, the BlackBerry battery is 1100 milliamp hours, and we'll define capacity, we'll define C rate over the next several slides, but understand that 1100 milliamp hours means that if you discharge this battery, if the battery supplied 1100 milliamps of current, it could do that for 1 hour, and that lets you kind of understand how much capacity, how much charge is theoretically possible out of a given battery. But then there's the iPhone 5 and iPhone 5S and 6, and you can see these different devices have more and more battery capacity. And this is not surprising to us as we continue to ask our phones to do more and more demanding things, operate larger screens, brighter screens, and communicate through GPS technology, this kind of stuff like this, that we really need a higher power battery to drive these type of applications. And then we move on, we take the same kind of technology that's in this cell phone battery, and we can scale it up into a laptop at about 5.4 amp hours, and then it's the same kind of technology again as we're stacking it up to electric vehicles. But it's not surprising to us that there's a demand for higher and higher capacity batteries. So that shows us one of the research trends and requirements. So the first one I want to highlight here is moving from R&D to larger cells and stacks to meet increasing requirements. So that may be new materials in the R&D level, and then it might be new studies within as we're starting to stack batteries up, right? So we have two segments of this market. One, people looking at new materials, often in a coin cell form factor. This may be on the order of 200 milliamp hours and 5 volts, much less material than you would see in a commercial cell. Next thing is we scale that up. We maybe larger voltages like a 48 volt pack for electric vehicle applications. Then we'll talk about state of charge and state of health, that's SOC and SOH, and the value on low impedance stacks. Here we're going to stress the need for impedance accuracy, the speed of EIS measurements, and the use of EIS to identify failure mechanisms. And then we will end the presentation with an overview of how we can provide spatial resolution to these measurements and kind of some in situ research test methods. So when we think about lithium-ion batteries, let's think about the generation of device development, right? So we think about battery materials, and this is where a lot of the R&D lives. This often happens inside a Glovebox in half-cell configurations, and it's people studying new materials for either cathodes, anodes, electrolytes, or separators. And we'll talk about solid-state batteries later on, and we'll talk about how their value in that one piece is functioning as both the electrolyte and the separator. Once we identify a material of interest, we feel like we have generated a new cathode or new exciting anode material, we will scale this up into either coin cells or 18650s, or etc. These are often completely sealed batteries, and now we can move the testing out of the glove box into back onto the bench top. These are often 2-electrode mode, but will benefit from having a third electrode, reference electrode, buried in there, and it'll let us do some advanced measurement techniques, and we'll talk about those later, such as getting the impedance of just the battery or the battery anode and cathode at the same time. But then we're going to use that technology, and we're going to continue to stack these things up. And here I call out stacking in higher current, but often it's stacked in configurations that give you either higher current, higher voltage, or both, and powers the product of current and voltage. And so that's really increasing the power, and that's where we start seeing stacked for high power applications. So here are some typical DC analysis techniques for batteries in particular. One, cyclic voltammetry, which is probably the most traditional, most fundamental electrochemical test method that we have across the board of electrochemistry. And people are specifically using CVs to study anode and cathode materials, and we'll show some data on the next slide. And as we look at mechanistic studies and really identify the voltage window that we're going to use for our charge-discharge experiments. Charge-discharge use a constant current to charge and discharge the battery. We're putting current into the battery as we're charging it, and we're taking current out of the battery as it discharges. It's going to answer questions for us like, what's the coulombic efficiency of the battery? Coulombic efficiency is coulombic is charge, and efficiency is how much charge am I getting out of my battery compared to how much charge I put into my battery. And of course, we want our batteries to be efficient devices, and so we want to use that as a key figure of merit, especially as we look at it over time. And the next one down, I'll call that cycle life, and that's really studying the capacity, so the amount of charge the battery can provide, not just on cycle 1, but on cycle 10, on cycle 100, on cycle 1000. And that's really what we want to see. We want to see, as we stress this battery with more and more cycles, how does its capacity, how does its ability to deliver charge change with cycle number. Next, we're going to talk about the effect of charge rate on capacity and cycle life. And so this is by varying the charge rate being current. And so when we talk about the pulse power applications, whether that's acceleration on a car or whether that's transmission during a cell phone usage, or bright screens, this kind of stuff, cameras, we're going to need pulse power. And pulse power is using higher current for a short time. And so we need to see how a battery is going to respond with that type of those type of discharge profiles, and so we can change the charge rate and capacity and study that effect on cycle life. And then it's the calculation and normalization of all the stuff to gravimetric capacity, specific energy, specific power. We'll highlight exactly how to do that. And then we'll walk through a slight variation on the charge-discharge technique. This charge-discharge with voltage hold, commonly referred to in the industry as a CC-CV step, and the first CC being constant current, and the CV being constant voltage, and that just kind of describes how that experiment happens. I'm charging a constant current, and then I'm doing a voltage hold before I do the discharge. This allows me to trickle charge the battery and make sure it's a completely charged state. As I'm holding it at that charge potential, I'm letting all the lithium ions from the outside of the material kind of solid state diffuse and fill all those interstitial sites in the middle, the core of the material, and to make sure the battery is completely full before we start the discharge process. So let's take a look at cyclic voltammetry experiments for battery materials. Again, these are often either half-cell experiments inside a Glovebox, or you'll see this sometimes in a sealed half-cell kind of coin cell type configuration. So how is CV? I told you CV is applied really to a lot of different types of electrochemical tests, but what's specific to cyclic voltammetry experiments for battery materials? First thing to highlight is the voltage window and the voltage scan rate. So the voltage window is quite large, right? So up here in the top left, I show scanning from 3.4 volts to 4.3 volts. So that's about a 900 millivolt voltage window. I'm going to make the scan at a very slow rate. So this is 0.1 millivolts per second. And so why do I scan so slow with lithium-ion battery work? Well, if I take that 900 millivolt voltage window and I multiply it by my 0.1 millivolts, or I guess divide by my scan rate here of 0.1 millivolts per second, that's going to give me 9,000 seconds to run 1/2 of one cycle of a cyclic voltammetry experiment. So about 3 hours, 2.5 to 3 hours to run that, to functionally charge or discharge that electrode material. And so from typical CV terms, that sounds like a tremendous amount of time. But if you think about it from a battery's application state, it's on par with what you would expect to be able to charge and discharge a battery. To fully charge, to fully discharge a battery in a 3-hour time. That's what we're representing here, and that's basically a 0.1 millivolt per second scan rate, or a C/3 discharge rate. The next thing I like to point out on these kind of graphs is that we think about batteries, we think about high power, we think about driving cars with these batteries, but this is at the R&D level of battery materials. And at this point in time, we're not building production scale quantities. And so when we do this, we're really at kind of a lowish, much lower current than what you typically see or may typically think of with batteries. The top left, I demonstrate this is less than 0.5 milliamp, so 500 microamps of current, and the bottom right, just over 1 milliamp of current. And that's really driven by the amount of material that we're using and the amount of material under test. Some very specific energy actions within VersaStudio that are designed to help with energy storage techniques. This combines energy specific terminology like C rate and capacity values for limits. The default instrument properties are tailored for slow scan experiments and tailored for these kind of higher currents that are often associated with the charge-discharge steps. We have specific graph templates that give you the ability to see capacity versus cycle number, Coulombic efficiency, power versus energy, all within the VersaStudio program. The value of that being not only does it save you from doing external analysis in a third-party graphing package, but it lets you see that analysis live, right? You can see what it looks like as the data is streaming in. We have a charge accumulation option for our CCCB step, delta resolution, which is basically a measure on change that allows you to take data at a faster rate when the response is changing a lot. And then we can do some complex signals based on power or resistance. And so if you think about you'll see when we show the discharge curve of a lithium-ion battery, it changes a lot at the beginning and changes a lot in the end, and is kind of a plateau in the middle. And so what a constant power does is it adjusts the signal based on the response. So power being the product of voltage and current, and so it will increase the current as the voltage decreases. And that's really how a lot of these devices really operate, because you're asking your battery to provide you a constant power to drive your device. So let's show some charge-discharge data step. This is a very simple experiment, but really represents how batteries are used in operation. So it's a charge step, and I'm going to charge, but instead of terminating the experiment at a given time, I want to terminate it at a given potential. And so that positive current is applied until the upper cutoff voltage is reached, and I get that cutoff voltage from those cyclic voltammetry experiments we showed earlier. And now my discharge. Discharge is the opposite polarity of current is applied. So I'm pulling power out of the device, and it may be the same magnitude of current that I charged at, or it may be different. Down here I have the equation for C rate also, right? You know, I said we normalize C rate to the amount of current required to charge or discharge a battery of a certain capacity in 1 hour, and so that's how it's a normalized current. So that's how a lot of battery people speak of this. So our CCCV experiment, this is what we were talking about earlier. You notice now instead of graphing potential versus time, I've changed the x-axis to capacity, absolute value of capacity. And the reason I did this is because I want to demonstrate the fact that when I'm charging the battery up to 3.8 volts here in this case, I did switch over from a constant current step to a constant voltage hold, and you can see that the capacity continues to accumulate as I am sitting at that 3.8 volts, and what that, the reason for that is that trickle charge. And so this is a demonstration of that experiment there. So here's a couple of these live graph types we can see streaming in VersaStudio. Top left is a potential versus capacity graph, and what this does is it's a charge and discharge steps overlaid on several cycles. And you can see on the discharge step, you can see that it starts off by giving you closer to 1100 milliamp hours, and then as the battery cycles, it starts to fade. And that's the capacity fade. That's really what you're seeing there. And you can see the capacity giving you slightly less and slightly less capacity on every discharge step. So one over in the top right there, we can see capacity versus cycle number. And this gives you the charge and discharge capacity calculated for you and based on cycle number. And you can see that impact of, it's basically a summary graph of all the graphs overlaid over on the far left. On the bottom left-hand corner there is the Coulombic efficiency of different cycles of the battery, and you can see the Coulombic efficiency starts off very high, meaning I'm getting almost all the charge out that I put into the battery, and then you can see around cycle 6 here in this particular test, there was a dramatic decrease in the Coulombic efficiency, meaning that I put in a lot more charge than I got out, and so that tells you that the battery is faded or may have caused some sort of issue that we can go in and study further with other advanced techniques. Other similar types of graphs, power versus energy, capacity versus time, these kind of data analysis are readily available as graph templates for you. I've got a single slide here on the importance of DC voltage accuracy. We talk a lot about not just can a potentiostat make a measurement, but how well can a potentiostat make a measurement, and accuracy defines how well a potentiostat can make different measurements. Every single experiment that you run, we measure voltage. And either specific examples here with the charge-discharge experiments is a galvanostatic control experiment, so my response is voltage, so I need to consider my measured voltage accuracy. But I told you the CCCV experiment, which is very common in lithium-ion battery tests, starts off constant current, but then I transition over to constant voltage. And when I hold the voltage, not only have I had to measure it, but I apply it as well. So now I apply a voltage and measure it back. And so now I've got two sources of error. So you can see those sources add together, and so it's even more important for a accurate DC voltage measurement. And then when we get to impedance analysis, and I'll talk about it in the next section, but when we do potentiostatic EIS in particular and define that versus an open circuit value, now I've got three different sources of error associated with my ability to measure DC voltage accuracy. So let's transition now and talk a little bit about electrochemical impedance spectroscopy. This is really my single slide highlight of what EIS is and EIS fundamentals. But for those of you that want extra detail on fundamentals of EIS or more, kind of blow this out into a more general sense, I'll reference our YouTube channel down here in the bottom link, and there's a very popular video there that highlights the fundamentals of EIS measurements. But I'm going to discuss it here as its application for energy storage devices, particularly batteries. Okay, so if I take an EIS measurement, it's going to use an AC signal. The resulting AC response has total contributions from different components, the resistive, capacitive, inductive, or diffusion elements of the sample. And what's very interesting, EIS is a high value content technique, and the reason for that is I can sweep the frequency. And I can by sweeping the frequency, I can see how the impedance responds, and then I can attribute the total response to whether it's acting as a resistor, capacitor, inductor, or diffusion. And the way I can do that is each one of these elements' response changes with frequency in a different way. So the impedance of a resistor is independent of frequency. The impedance of a capacitor varies inversely with frequency, meaning its impedance is low at high frequency and its impedance is high at low frequency. In an inductor, it varies proportionally with frequency, meaning that if you scan, if you sweep the at high frequency, the impedance of the inductor is high, and at low frequency, the impedance of the inductor is low, and you'll see all of these things kind of come back around when we start looking at EIS data for lithium-ion batteries here in a little bit. So this slide, I've titled it Signal versus Response, or Response versus Signal. And the reason for this is I want to talk about the different modes that you can operate electrochemical impedance spectroscopy in. Electrochemical impedance is always the ratio between voltage and current. And so it's defined by this equation of Z equals the AC of voltage divided by the AC current. Now to be valid, there's some criteria of EIS data. One, it is that the system is linear. And you'll see that if A equals B, then 2A equals 2B. And what that means is if you double the size of the signal, you double the size of the response. And since it's a ratio, the impedance doesn't change. Now, on the extremes, you can go to very high signal and drive nonlinear responses. And if you try to apply a signal that's too low, it may be noise dominated. So really, that's the idea of linearity to be valid. Is you need a signal that's kind of generates enough signal to be measured, but not enough to drive nonlinearity in the system. We want the EIS data to be causal. And this is causal like cause and effect, and this means that the response is only due to the signal applied. They don't have any background there. It's complicating my measurement. We need experiments to be stable, and so stability, when we look at some of the data, will show a lot of the information we're going to get are at lower frequencies. Lower frequencies take a longer time, and in doing that, we want to make sure our system is stable. We'll talk about some different techniques and demonstration of how we figure this out and ways we can kind of benefit from that over the next couple slides. But assuming that all of these are valid, then the measured impedance should be independent of the mode of operation, meaning that if I'm controlling the potential in the EIS experiment or controlling the current in the EIS experiment, both should give me the same impedance, because it's either a ratio of signal to response or response to signal, and the answer should not be dependent on the two. So why do I bring this up? Really because we want to study some of the, or I want to highlight some of the benefits of galvanostatic EIS. So this is EIS under galvanostatic control. So the first thing I'm going to say about this is, I told you that constant current's really how a battery is traditionally used in practicality, right? In its real function applications. And so if I can stay in galvanostatic control, that's already one benefit. The user gets to define the stimulus and DC levels so that current overloads get avoided. What I mean by this is the impedance of batteries are low. Right? We'll show this. We'll show impedances below 1 ohm and often below 1 milliohm. And when we think about that, if we don't already know the impedance of the battery before making the measurements, and I start putting a voltage on the battery, if the impedance is low enough, I very well may overload the current capability of the system. But really, when I think about what the value of galvanostatic EIS is versus potentiostatic EIS in the application of low impedance systems, it's the fact that potentiostats have many, many current ranges. And by having many current ranges, it means that I can select a very appropriate current range to give me high resolution and accuracy and low offsets compared to the signal level. If you look at the specifications of a potentiostat, because we have so many different current ranges, the accuracy of the resolution and accuracy is much better on current measurement than it is on voltage measurement. So let's demonstrate this, and I'm going to demonstrate this first with a dummy cell. I see tremendous value in dummy cells because it lets me validate my system and validate my experiment. But not every dummy cell should be the same, right? When I'm building a dummy cell to represent my low impedance systems, I need to build it out of low impedance devices or low impedance components. This is not you don't want to put on a mega ohm or kilo ohm resistors if we're trying to see how we're trying to optimize test conditions for a battery, right? Let's build a dummy cell with a 0.1 ohm resistor or 100 milliohm resistor in series, and our 1 ohm and 100 microfarad capacitor and resistor in parallel. And we can, again, that fundamental EIS presentation can walk you through construction of this Randall cell and speak to you about each and every piece. But here I want to show what I did is run this experiment on that dummy cell, both in potentiostatic control mode and galvanostatic control mode. And so the red is not a fit of the blue line. It's the fact that the blue points were acquired in potentiostatic control, and the red line was acquired in galvanostatic control. And here I'm using this graph to demonstrate the same response whether I'm in potentiostatic control or galvanostatic control. So that validates one of the things we had said earlier. Next thing I want to do is look at the effective stimulus level, right? And so we talked about linearity. And how do I decide what stimulus level to select? Well, I can come to my dummy cell here and change the AC stimulus level and look and see the values of the responses. So in this region on this dummy cell, I start off with blue dots back here that you can't see because they're behind the red data line. But the blue dots on the 10 milliamp current stimulus looks perfectly smooth, and then at 1 milliamp I decreased it and it overlays it perfectly. And then as I go down to the 100 microamp on a stimulus level in this cell, you can start picking up, you can start seeing at this highest frequency, you start seeing the impact of too low of a signal as it starts kind of bouncing around beyond 10 kilohertz. So this is a great way for us to validate system measurement and help us get an idea of where we can start with signal level for our impedance analysis of our battery system. But again, and I appreciate that while I can learn a lot about my potentiostat through dummy cells, eventually we're gonna connect this up and we're gonna test a battery. So this is a commercial cell phone battery. It's not a brand new battery, but it's a battery directly out of a BlackBerry. And I ran a galvanostatic EIS experiment at 100 milliamps RMS or 100 milliamps signal level. And what I like to do here is show the table after you take the data and fit it through equivalent circuits, and we get the equivalent series resistance. ESR is one of the real figures of merit for lithium-ion battery manufacturers and capacitor manufacturers, because you can think about that series resistor. I think about it really almost like an inefficiency. It's the resistance that has to be overcome in each charge and discharge process, and in doing that, you are losing efficiency. But I do know that impedance spectroscopy it's an intimidating technique for a lot of users, and the thing that becomes intimidating with it is building equivalent circuits and doing modeling and adjusting parameters and finding start parameters and uncertainty levels. So the other thing I want to show, and again we talk about this a bit when in the fundamentals presentation, is when you go in here and you can look down and just look for the point where in the Nyquist plot when it crosses 0, where the Z imaginary is 0 and I'm completely Z real, and so that's a completely 0 degrees phase shift, so a completely resistive component. And we can see when we fit the data, I got 153 milliohms by fit, and when I just highlight the point that crosses the 0 axis, I got 151 milliohms. And so a pretty reasonable close approximation of my ESR, really just graphically, without any added complication of using equivalent circuit modeling. So all this information is available for you, higher content, technical content available for you through the circuit modeling strategy, but I want you to understand that you can benefit a lot from impedance analysis if you're looking for key figures without going to that level of detailed analysis. So one of the values of working at AMETEK is that we're the largest supplier of electrochemical test equipment in the world, and in saying that, we have applications teams in a lot of different regions, and so some of these data we see here were supplied for this presentation from our China team. And so there we went and took a Solartron 1287, 1260 with external booster and connected it up to a large single cell. When I say large, this is a 100 amp hour single cell. So this is truly something on the level that would work in an electric vehicle. So two things that I like to call out when I look at this graph. Number one, you can see the highest frequency point is 1 kilohertz. So this is much lower frequency than you would see in other types of batteries or other types of applications. So the starting frequency is 1 kilohertz and continues lower and lower from there. The other thing I like to point out is the magnitude of the impedance. You can see here that is probably 600 microohms. A lot of your data lives below 1 milliohm of impedance. And so this is going to stress the need for accuracy within the impedance measurement capability, not with bandwidth and accuracy that play together to be able to make this type of measurement. And so we'll talk about that over the next couple slides. And it'll be a recurring theme of accuracy to be able to project small, to measure small changes, because we're going to project those outwards. So this is a way that you can measure the response not just of your potentiostat, but your potentiostat through your booster. And so this is connecting up just a 100 milliohm resistor and sweeping the frequency. So I told you before that the impedance of a resistor is independent of frequency, and so you would expect that it would be this nice flat curve right at 100 milliohms all the way out the entire frequency spectrum. But when you get to the highest level of frequencies, you start seeing the impact of a low bandwidth filter, of a low bandwidth booster. And so what this shows is the red line. This was with a high current potentiostat and no booster, but you could imagine a high frequency, high bandwidth booster and the impact it could have, because I get much longer frequency, much higher frequency. I can go to much higher frequencies with either high current potentiostats and no boosters, the ideal, or a high bandwidth booster coupled into that technology as well. And so what we need is boosters. If you think about it, I've put this booster, between my potentiostat and my cell. And so you have to understand the limitations of that booster in your measurement anytime you're making those measurements. And really, you can see the value in this type of experiment of high current potentiostats and having that high current built in to the booster. So let's go back here now and let's talk about a problem that people are using, a real world problem people are using impedance to solve. And this is the state of charge, and I've got up here the cell phone battery indicator of 90% up there in the top right hand corner, because we're all used to cell phones. But you can think about the state of charge as how much charge is left in my battery. And when we think about this in electric vehicle application, you can see the importance because the state of charge is functionally a measure of your gas tank. How much charge do I have left in my battery, and am I going to be able to get to my destination or not? So this is a true real-world problem. It's critical to make a determination from this, and we're going to use impedance analysis to do it. And in doing that, we're going to see how the value of accurate impedance analysis. So what I did is I took one of these 18650 batteries, right, and I took it over to one of our potentiostats, and I first charged it completely with a CCCV step, and then I ran an impedance analysis on it, Galvanostatic control EIS. And then I systematically discharged the battery 10%. And so from 100% charge to 90% charge, and took another impedance scan, and then 80% and took another impedance scan, and then 70% all the way down to a fully discharged state. So a couple things I'm going to take away from this. Number one is that you can see a systematic change in the total impedance as the battery discharges. It's not surprising that the battery's impedance grows as the battery is discharged. And look at where the impedance changes, not just that it changes, but at the highest frequencies in the inductive region and the ESR region, they look to be, don't change very much with frequency. But when we go to lower frequencies, we can start seeing that is where the impedance changes with state of charge. So if I'm building basically a state of charge sensor, I can do so using low frequency EIS. And that's what I've done here with products from our MODULAB platform, doing single sign impedance at 50 millihertz, so a fairly low frequency, and that we're studying here, and we can watch the state of charge change, not just at the total sweep, just running impedance at that low frequency. And that's really how these things work, right? You are basically going to sweep the frequency until you find a characteristic frequency where these changes happen, and you're going to build a sensor, and you're going to investigate that frequency over and over and over, and tie that directly to state of charge. And then you will know going forward that if you have 0.13 impedance level, you can roll over here and scroll down and on our calibration curve basically and find out we got 40% state of charge. So to do that, I used products from the AppsLab series, specifically the EnergyLAB and EchemLab. These are the newest performing, the newest instruments from the Solartron Analytical line, and both of them include onboard EIS capability with the ability to measure micro-ohms of impedance, and we showed the value of that in these larger batteries as they start growing in size. The BlackBerry battery was hundreds of milliohms, and then the electric vehicle battery was less than a milliohm. 4 auxiliary electrodes associated with each one of these product lines, and this can be used to study anode and cathode impedance separately, and this is really of high value. And I told you early on about how we can build reference electrodes into our batteries for diagnostic and purposes and studies right here, and we'll walk through how you would do that and to measure the impedance of the anode and the cathode separately, or cells within a stack. Both are capable of multi-sign EIS. Multi-sign EIS will apply a series of sine waves to your battery at one time, and so it's a much faster EIS test method. Got some data we'll see in a little while where the data acquired through multi-sign is 5 times faster than data acquired through single sign. We're capable of a wide variety of boosters, all the way up to 100 amps and all the way up to 100 volts, and the MODULAB series here allows further expansion for material studies. And really, when I think about that, we'll talk about some of the solid state battery applications and where you can see overlap between those applications. We can take calibrated resistors and come in and look at low impedance measurements and build them up, again, basically dummy cells, and determine the amount of noise and accuracy and repeatability we have in EIS measurements. If I take this high quality EIS measurements in this region, you can see that this is 1 milliohm down to a 100 microhm level. And if I take all of that, if I take those and continue to run those at different calibrated resistor levels, we can build up what's called an accuracy contour plot that defines the impedance accuracy here. So the highest accurate region of 0.2%, and then you can define both the impedance range and the frequency range over which you have different levels of accuracy. Really, when we circle the red circle here is really where the impedance is important for researchers in the energy field, right? If simply stated, if you have a high impedance battery, it's not going to be a very well performing battery. So let's take a very similar experiment that we just did for state of charge, but let's look at it as state of health. And so state of health basically studies how the degradation in a battery. Right? My comparison here is that you plug up your laptop on day one after you have your laptop, and it tells you have 4 hours of battery life left. Not a problem, you get all 4 hours. After 1 year of usage, when you plug up your laptop and you unplug it and it tells you have 4 hours of battery life left, after 30 minutes it's telling you, warning, you're running out of battery. So what's happening is the computer consuming more power? No, what's happening is your battery has faded, and it's not as strong as your battery was from day one. And so while that's okay for commercial products, I guess, we've grown accustomed to this and we understand this. When we start scaling these batteries up to electric vehicle level, the value of the battery becomes such a huge part of the value of the car. It becomes important to understand how batteries perform versus from day one, from virgin state, right? And so I'm going to take a 500 milliamp hour lithium ion phosphate battery. I'm going to cycle it at 5C, pretty high rate, because I'm going to try and show degradation here for 25 cycles using CCCV, and then I'm going to study it under these test conditions. Importantly, I'm going to run a multi-sign because I'm going to run to 10 millihertz, reasonably low frequency. And all of this is documented in an application note published on our website. So really, this is what I said. I'm going to charge up to 4.441 volts, then swap over to the constant voltage, and I'm going to determine something called state of health, and it's going to be a ratio between the amount of charge that I delivered on first cycle versus each subsequent cycles, right? So by definition, then, I have 100% state of health on the first cycle, and then as the capacity fades, as I'm giving you less and less capacity at each cycle state, it's going to provide you a lower and lower state of health. And so this really, if you think about state of charge, is how fully charged is my battery in a one cycle. This is at a same state of charge measured over and over, and it's how it's long-term health of the battery. So to do this, we want to correlate this to a state of health, or to some measurable parameter, just like we did with state of charge. And so these are state of health determined at 3 different states of charge. And simply stated, the more accurate you can make your impedance measurement, the better you can make this measurement. The better you can quantify your state of charge and state of health measurements. We talked briefly about a multi-sign impedance because it can take data faster. And this shows a 5x experiment duration when using multi-sign EIS versus single sign EIS. This is important because a lot of the diffusion controlled processes happen at lower frequency intercalation of batteries, and so we want to get that. We're going to get that data as quickly as possible. So let's talk beyond lithium-ion batteries into solid-state materials or solid-state batteries. And the focus of research is moving here because it's considered safer than organic electrolytes. A lot of the carbonates and fluoride salts and stuff used in traditional lithium-ion batteries can be removed when we move to a solid-state battery. But temperature range is also very important because we can work at a wider temperature range with solid-state materials, and it helps energy density because one material can operate both as the electrolyte and the separator, and they have a larger electrochemical window than organic. So those are some bullet points of why interest is going into solid-state batteries. We can take here and scale out, and we can look at, as you look at the the Nyquist plots, the impedance spectra, though, as you look at these different materials, the capacitance is so low that we need to really push it out to a higher frequency to get the full characterization of the high frequency semicircle. And so if you know these values, you can kind of go back and put them in and kind of do a calculation out and figure out, you know, what type of specification, what type of bandwidth do you need out of your potentiostat to make these type of measurements. And often this exceeds 1 megahertz in the solid state battery world. And here's another picture of the Solartron 1260A. It's our frequency response analyzer, and it's the most published, most cited FRA for electrochemical impedance studies in the world. And so I've picked out a couple of Nature papers here that just kind of just demonstrate the fact that you need high frequencies to study solid state batteries. And so this goes to 8 megahertz in studying those solid state batteries. This one, you're running a 1260 and a 1268, 1287 combination, and when you're looking at just that solid state material, it's up to 12 megahertz. So I said a hot topic is high voltage battery pack testing, right? As we start taking this technology and scaling it up for lithium-ion batteries to be used in electric vehicles, the one things we're going to do is we're going to stack these batteries together. So the requirements of the system is the ability to measure high voltage. It's the requirement of impedance accuracy we talked about. We'll talk about auxiliary electrometers. And so an electrometer is a electro, meaning voltage, and meters being measured. And so it's a way to measure additional voltages. And we're going to talk about the value of that in a little while from a failure analysis standpoint. And then we're talking about a range of external boosters that are available. So I'm going to call this basically this is the value of the auxiliary electrometers, and I'm going to talk about impedance. I'm going to talk about basically sub-impedance. And so if you took the impedance of each one of these little batteries in a stack and you added the impedance all together, you would get the impedance of the entire stack. So in a traditional electrochemistry experiment, if I want to get the impedance of the stack, I'm going to connect to the two ends of the stack, and I'm going to measure the voltage and current across the stack. And that's going to give me the impedance of the stack. But if you think about the current flow, current is rate of electrons, and so one electron goes into the stack, one electron is going to come out. And so that means the rate that electrons travel through the stack is the same everywhere. And so that means the current's the same everywhere. And so that means instead of just measuring current, if I can measure voltage as well, what this is going to allow me to do is measure not just the entire stack, but come across and measure each individual cell in the stack. And that's going to give me the ability to look at which one of the cells in the stack is dominating its impedance. So basically which one of those cells is failing. So the exact same type of experiment happens in the anode-cathode experiments we were talking about earlier if you have a reference electrode. What that allows you to do is separate out, same kind of thing, the main channel measures the impedance of the entire cell, and then the auxiliary electrometers connect in and measure either the voltage of just the anode, just the cathode. And in knowing the total current, we can get the ratio of voltage and current, and that's going to give us the impedance of the entire stack and the impedance of each individual cell or anode cathode, depending on where you are in that development cycle. Okay, so let's take a MODULAB ECS and put a booster on it, and let's study not just a stack of batteries, really, but it's a stack of stacks of batteries. And so each one of these green cells over here is an 18650 battery, and we have several stacked up together and several of those stacks put together. And so what we've done with this plus our booster is demonstrated the ability to measure the impedance of each one of these stacks individually, and then the red line there is its sum of all the impedances together. And so you can see in this commercially available stack, this big battery, what you can see is the entire impedance of the stack is on the order of 6 milliohms. So you can see why it's important to have accuracy. You know, if that was that's why it's so important to have not just EIS accuracy, but the ability to have the highest level of accuracy at these lowest measurable values. And you can see the what is that, green, blue, and purple and lightish blue here, you can see the impedance of each one of those stacks. And so you can see slightly that the blue stack, stack B, has a little bit higher impedance than the rest of those other stacks. So that's the one that's dominating the impedance of the stack. So we talk here, we can see the differences of EnergyLAB and EchemLab, and how EnergyLAB has a 2 amp capability built on board, and how that allows us to test some larger single cell batteries. And then when we start talking about EchemLab, we start talking about the 100 volt capability, and that allows us to start taking some measurements all the way up on stacks. Both of these are compatible with boosters, and so we can configure that either in high current or high voltage mode, depending on your given test requirements. Another multi-channel platform that we have is our PARSTAT MC. This is a chassis platform. It's tailorable with 3 different types of potentiostat modules. The newly introduced PMC 200 provides us the highest resolution measurements and highest throughput with 2 channels per card. The PARSTAT PMC 1000 provides us 2 amps per channel, as well as booster capability, LCI capability to expand its current ranges. And the PMC 2000A provides us both high voltage, 30 volts on board, and 6-wire capability. So that's 1 additional electrometer when we're making those measurements, so it's capable of doing anode-cathode tests or a single cell within a given stack. So I can take that PMC 2000A and run this seemingly simple experiment, but the 30 volt stack, the 30 volt capability gives me the ability to stack 2 9-volt batteries together and make a open circuit measurement of more than 19 volts, and very few potentiostats in the world can do that without having a booster attached. Here we can run this as a 6-wire measurement then on these 2 electrode stacks, and we can see the impedance of the entire stack is generating about 1 ohm of impedance, but we can see that 1 battery is generating 100 milliohms. And so if 1 battery is generating 100 milliohms and the entire stack is generating 1 ohm, that tells me that the other battery is generating 900 milliohms, or 90% of the stack impedance, and so that's telling me it's what's failing. So from an engineering side, you can see that's the battery is failing. If you take this and think about it as anode and cathode work, if you knew whether the anode or the cathode was having the largest impedance and driving the impedance of the cell, you would know that's the one that needs to be optimized. So let's transition and let's talk about test methods for electrochemical supercapacitors. And so these are going to be fairly large capacitors. I'm going to use a PMC 1000, and I benefit from the fact that 1000 can both supply and measure 2 amps without any booster attached at all. So I can take this 50 farad capacitor and I can sweep it through CV at 10 millivolts per second. The CV is going to give me the axes of voltage and current. I multiply those 2 together, normalized by scan rate, and I get up to 90 coulombs per charge discharge. And then when I divide that by the voltage range, I can get to the capacitance. And this 50 farad capacitor nominally gave me 53 farads through cyclic voltammetry experiment. And this is a show of the integration capabilities of VersaStudio there to make those measurements for you. Now when I start increasing the scan rate, I go from 0.1 millivolts to 10 millivolts to 25 millivolts. Even this 50 farad capacitor, when I sweep it at 25 millivolts, I'm at well over an amp. And our platforms of the PMC and the cell test are some of the very few multi-channel potentiostats on the market that have the capability to make this measurement without any boosters attached at all, because they're high current capabilities. Speaking of current, we can do constant current, constant discharge to charge and discharge that capacitor. Here we're going to charge and discharge it using a constant current, and we can measure that capacitance value then over that voltage range at 51 farads. Let's look at even a larger capacitor at a 3000 farad capacitor, and using cyclic voltammetry to do this. As the size of the capacitor goes up, I need a booster to run these types of experiments. But I'm gonna leverage the PMC platform and mix and match capability to put the PMC 1000 together with its 10 amp booster, and I'm gonna run a cyclic voltammetry experiment. And even at the slow scaling rate of 2 millivolts per second, you can see I'm more than 7 amps of current coming through there, and I can integrate it much the same way and get a value of 2,700 farads. When I run this again through constant current charge-discharge and use 10 amps to charge and discharge the battery, we can see again, what is that, 2,500 roughly farads, similar to what I got from CV, and I can use our data math function within VersaStudio to convert the capacitance in real time over to farads. Certainly, capacitor research benefits from electrochemical impedance spectroscopy as well. You can see a very simple Randall cell type design here that we have for modeling this data. Again, the equivalent series resistance in series with the value of the capacitor in parallel with a leakage, the resistance due to leakage there. And here is the response both in Nyquist and a fitted Bode plot. And we can see it resembles the impedance of a capacitor, right? As we decrease the frequency, the value of the impedance increases. And when I go over here and I look at kind of where the value of the equivalent series resistance estimate directly from the file, I can look down and see that it's 14.7 milliohms, and this commercial device is specified at less than 20 milliohms of ESR, and I can fit that data to 49 farads, very close to the 50 farad capacitor that the anomaly is with this commercially published value. Similar kind of thing happens with a 3,000 farad capacitor. I need to use a larger, or I do use larger signal to optimize that measurement. I use a 1 amp RMS signal, and I can fit this data to 3,200 farads, and I fit the ESR to 8 milliohms. Much like the battery we saw with electric vehicles, it starts getting to very, very low values when you start looking at that type of application, when you start scaling it up. We can see that we have a lower ESR in these larger commercially available devices here at 8 milliohms. Go back and talk about our dummy cell and how we get to validate measurements, because when I say things are 8 milliohms, I start thinking to myself, well, how good is this potentiostat? Like, is this something that am I ever reached the floor of the potentiostat measurement capability, or is this 8 milliohms really truly from my cell? So to study this, I can come in and take a calibrated 10 milliohm resistor, calibrated 1 milliohm resistor, do EIS experiments on these values, on these components, right? And so these line, the red and purple line, that's actual true data. Those aren't just drawn theoretical lines. That's true data measured through the same setup with 1 milliohm and 10 milliohm resistor values, and you can see that I can, with accuracy and over this bandwidth, measure these two values, and the fact that my EIS signal lives between the two gives me confidence in my ability to actually measure that capacitive value for that large scale supercapacitor. So we talk about not just batteries and fuel cells, batteries and capacitors, but this is a discussion on fuel cells, and I touched on this when we talked about, in particular, EnergyLAB's 100-volt capability with its auxiliary electrometers to go in there and pick out different cells within large stacks. But also this other segment of fuel cell research is in the catalyst itself. A lot of that's done with rotating ring disc electrodes and bipotentiostat work. A great option for that is our PARSTAT 3000 ADX. It's the world's highest performance bipotentiostat. We have two fully functioning channels, both capable of electrochemical impedance spectroscopy. And so we can use this to evaluate the catalysts that are being used in fuel cells through our rotating ring disc experiment. Entire product line devoted to the study of solar cells through either our PHOTOECHEM DSSC modules within our MODULAB platform and our SolarLab, which is a fully integrated SolarLab test station system. Also, MODULAB, I talked about its ability to study cells at this level, but also make materials measurements on solid oxide fuel cells. Next, we'll transition to the scanning technologies and in situ measurements. And so really the goal of scanning technology is to provide spatial resolution to different electrochemical and materials measurements. This is our VersaSCAN. It's a completely piezoelectric motor controlled positioning system capable of scanning large samples with high resolution. And so this is, to put numbers on that, it's 100 millimeters on every axis with down to nanometer level resolutions. But to apply this to lithium-ion battery studies, we've got some images here from one of our partners in Germany, and they've highlighted their success of integrating a VersaSCAN into a Glovebox and the connections here. And the reason for that is, I said that lithium-ion batteries achieve their high voltage windows and high power by not operating inside an environment full of water, right? So I can, by removing water, by removing oxygen from the platform, I can get these high voltage windows. But that means when I'm using scanning probe technology, a lot of that happens inside a Glovebox, where it's full of argon, and so it protects the system from ambient water or ambient air. And so what they were able to do is demonstrate all the advantages that I showed you of electrochemical impedance spectroscopy to study state of charge. They were able to demonstrate this in a local way. And so what we did here is we worked with a probe and measured voltage drop in solution and tied that back to electrochemical activity. So here's local impedance responses at different states of charge and different positions across the electrode. And so much like when we did the state of charge analysis in a bulk format earlier, what we're doing here is we're looking to identify a given frequency that we can come back and make that measurement and make that data map. This is that data map at low, medium, and high states of charge, and we can visually see, we can provide spatial resolution to where the impedances are changing on the electrode surface throughout the processes, right? And so a really high information content technique of impedance spectroscopy coupled with scanning probe technology to give us a spatial resolution. We have systems installed all over the world inside Gloveboxes to make these type of measurements. There's much fewer published references on this, but it's a world of exciting possibilities for this type of research. Other examples of partnering our MODULAB platform with in situ type electrochemistry to study lithium-ion battery mechanisms. Lithium sulfate battery here combined with our MODULAB to study electrochemistry Raman. And so we can look at the valence changes of the sulfur during the charge and discharge step. We've got some battery holders for different battery form factors, and you can see a picture here mounted onto our PARSTAT MC. So one of the values is simply that it's a cleaner, or like to say cleaner lag, cleaner signal. And so a cleaner lab meaning that you can remove the cell cables. This goes in place of the cell cable and connects directly to the front panel of the potentiostat. The real value here too, though, is the fact that you don't need an extra cell cable to get to the battery. And I told you these impedances are low, and so when you put on large, long cell cables, it provides additional opportunity to pick up noise or inductance or have other things that just kind of limits the success of the measurement. And so to optimize that measurement, we can remove that cell cable and make measurements directly at the battery. So thank you for your attention. Today's presentation on electrochemical test methods and products for the evaluation of lithium-ion batteries and supercapacitors. We talked about a lot of different products within the AMETEK SI portfolio. We talked about products both from Princeton Applied Research and Solartron Analytical and their applications to DC, AC, and localized test measurements for these. If you have any questions, here is my email address and contact information, and thank you for your attention.